Okay, folks, welcome back. We're going to talk a little bit about ice tables this morning. Excuse me. And that was part of some of the questions in 7.1, and it might have been giving some of you some trouble. Um, Ice table is just a tool that we can use to analyze an equilibrium system. So we're going to start putting numbers into the equilibrium system and try and do some stoichiometry, calculating what's left or what's in the beaker, what's in the flask at equilibrium. So if, just as a sample here, we have um, reactant A plus reactant B. Sorry, we need to balance this. So it should be 2AB and 2B. So A2 plus 2B will form 2AB. That reaction is an equilibrium reaction. We see the double arrow here. And when it occurs, at equilibrium, which is when we're usually interested in finding out how much is in the beaker, we're going to have all three of these things present at equilibrium. You're going to have some A2, some B, and some AB. And so it's a little different now with stoichiometry. We don't limit anything. Everything is present. In fact, if it's not present, then it's not at equilibrium and we can't really analyze it. So all of them have to be present at equilibrium. In these first questions, we're going to be given the initial concentrations, like how much was put into our closed system to start. And then as long as we're given either what the change in one of those products or reactants is, or the equilibrium value of one of those products or reactants, we can just do some basic stoichiometry and fill in all the other blanks on this table. It gets a little more complicated when we're not given one of either the change or the equilibrium values, but there is a way, and I'll take another video and we'll take a look at that tomorrow. I'll try and post that so you can see how you could do this without having either C or E values. But for now, these first couple of questions, we're going to look at what we can do if we're given some data about the equilibrium that's set up. Okay? So I posted these two lecture questions. If you want them, you can print them off. They're on the classroom. Let's just go through this a little bit at a time, and we'll try those two questions as we work our way through this. So products and values, reactant values can be calculated at equilibrium. So it's just at equilibrium. That's when we can calculate them. That's when things have become macroscopically stable. So that number, the numbers in terms of concentration, are not changing at equilibrium. We know that there is a constant back and forth of reactants forming products and products forming reactants, but the equilibrium, at equilibrium, the concentration of those two things macroscopically remains constant. Right? So being able to use that idea that everything is kind of remaining constant at equilibrium, we can go through and we can calculate what the concentrations are at equilibrium. Now you're going to use some basic stoichiometry. So you'll have to go back and remember kind of how to use a balanced chemical equation, how to move things from one point in an equation to another point in an equation, and we'll take a look at how we do that right now. And then, as I said in the little intro there, we're going to try and do some questions today anyway of if one of the entities changes and we know how it changes, we can calculate all the other ones. Hopefully that kind of makes sense from your previous work with stoichiometry. Or if we know the equilibrium value of one of them. Those are the two we're going to work on today. We'll leave this one until the next video. There's a fair bit of, this one's a little more involved to be able to answer. So we'll just work on these first two today in this video. Okay. This first question is very characteristic of what you were trying to answer in section 7.1. And you'll be given information about the reaction. This one says, consider the following equation for the formation of hydrogen fluoride from its elements at SATP. So equilibriums are established at a certain temperature and pressure. And SATP just means standard ambient temperature and pressure. It doesn't really matter what those temperatures are to us, as long as in the question those numbers remain constant. So usually it says, it may not say, but if you're working at something at equilibrium, the temperature and the pressure have to remain constant throughout the time that we're calculating. If that changes, the equilibrium balance actually changes. As you know from the last unit, that temperature can speed up the rate of a reaction, and it doesn't speed up the forward and reverse reactions equally. So we end up with a new balance point. So we're always going to look that temperature has been maintained at a constant in each one of these questions, or none of the math works. And so here's our equation. H2 is a clear colorless gas. So this is colorless. F2 is a brown gas. So it's very easy to see it. And we can use that color intensity to measure its concentration. That's actually how we know if there's F2 being made, the flask becomes brown, more brown, a darker brown color. And if F2 is being used up, it's being turned into HF, which is colorless. We see the brown color start to decrease. And we can use that information. We can gather that by using some lab data or lab equipment that can actually measure the intensity of the color, and we can convert that into a concentration. So just so that you know that it's possible to do it, we will always be given the concentrations, obviously, but if you were actually to do this in a university lab, you would be using some what's called a spectrometer, and you'd be able to match the change in color to the change in concentration and actually measure it, in this one at least, because of the brown color, which if it goes in, we make more F2, it'll be browner, and if we make less F2, that brown, orangey brown, it's actually an orangey brown color, will actually go away. Okay. So it says here, if the reaction begins with 2 moles per liter concentration of H2 and F2. So we'll typically be working in concentration. You'll remember in last year in grade 11, we would have worked in moles, but often remember these things are occurring in a closed system. So as long as your system is closed, and it's not changing shape, and they don't even tell us how big the system is in this question, but as long as that volume is also constant, then we can simply work in concentrations. We don't have to change these concentrations into moles and then move the moles like we did in grade 11 and then turn it back into concentration. As long as the volume is fixed, which it is if this is an equilibrium system, we can't have the volume changing either. We have to have the temperature, pressure, and we have to have the volume of the container fixed. Then we can just work in concentrations. We're going to get the same ratios, and because the volume's not changing, there's no need to switch this back out into moles and then come back into concentration. It's just a bit of an easier step. You may see some videos if you watch some things on your own that show this being put in as moles and then doing a calculation at the end to turn it into concentration. I generally just skip that step because as long as the volume doesn't change, there's no need to go through that extra step. Okay, so we've got 2 moles per liter of both of the beginning gases and none of the end gas. So from an equilibrium point of view, that tells us what's going to happen. If there's these 2 gases are present and this one's missing, then at the beginning of this reaction, the forward reaction is going to be the only thing happening. And so that's going to be the fairly fast reaction. And at the very, very beginning of this reaction, just as HF starts to get made, the reverse reaction is going to be fairly slow. Now, that means that overall, what we're going to see is a shift in these concentrations. The concentrations are going to shift from the reactants toward the products. And eventually, the forward and reverse reactions will come out to be equal. But at the beginning, since there's only reactants present, the reaction will shift in the direction of products, is what we say. So there's a net movement to make HF until those 2 reaction rates become equal, and then we don't see any changes anymore. But the shift would be toward the HF. So as soon as we put these 2 chemicals into the flask, it's going to shift in the forward direction, and it's going to try and make some HF. Now it goes on to say that, and at equilibrium, if the equilibrium concentration of F2 is measured to be 0.48 moles per liter. So using a spectrometer, they've been able to measure how much of this is left, and it's 0.48 moles per liter. Remember, we started with 2, so some of it's been used up, and that's shifting to the right, shifting into the forward reaction, and we only have 0.48 left. But that's all we need. If we look back at our list here, to be able to solve this, we need to know how something has changed or the equilibrium value of one of the things in the reaction. And so we have that. We have the equilibrium value of this one, 0.48 moles per liter. So the first step then is to set this up into what's called an ICE table. So ICE just stands for initial, change, and equilibrium. So the 3 states that our reaction could be at. We could have it just before we start. We could have it while it's shifting. So the change is describing the shift that the initial setup undergoes. And then equilibrium is when we're back at a balance point. So this is when forward and reverse reactions balance each other. Okay, so what we do is we take these, we're just going to put these at the top. So this is where our H2 goes, our F2 goes here, and then I'm just going to put a little set of arrows here just to remind myself that's where the arrow is in the equation, because it's important to tell reactants from products. And then I'm going to put the HF down here. Okay. And then let's fill a few things in. So we look at our data. Remember, the data said that there were 2 moles of H2 and F2. So we can go in here and in the initial line, we can fill in 2 moles per liter, 2 moles per liter. And then this was 0. There wasn't any of this there when we set up the flask. Okay. Then it underwent a change. Well, we know then that the shift that it underwent, it shifted in this direction because all we had was reactants. So the equilibrium would have to shift toward the products to eventually come to a balance point. So we know we had a shift in the forward direction. And then there's some kind of change happened here. Now, we're not told what the change is, but we are given one other piece of data. We're given that the F2 was measured and found to be 0.48 moles per liter. So down here, the F2 is 0.48 moles per liter. Okay, so that's the setup for the data table. And that gives us everything we need to fill in. What we want to find out is what are the other ones remaining? What are their equilibrium concentrations? So we'd like to know how much H2 is there at equilibrium. We'd like to know how much HF got made at equilibrium. Those are the 2 that we're trying to fill in. And we do this just like we did stoichiometry in grade 11. We just work our way through by following kind of a pathway. So what we can do here is we can back up and we can take a look at this reaction here. And we realize that if we ended up with 0.48 moles per liter, then this had to be 2 moles per liter, the change, and then you had to subtract something, right? So that must have gone down. So we must have subtracted something or used up some of the 2 moles per liter. Question is how much? Well, we have 0.48 left. We started out with 2 moles per liter. So that means that we have we must have used up negative, I'm going to put a negative there because we used it up, negative 1.52 moles per liter. Okay. And then if you look down this column, 2 plus negative 1.52 is 0.48. We can add down these columns. And if you take the initial plus the change, you should get the equilibrium value, which is 0.48 moles per liter. Okay. So now that we have this change here, we can use what we know about molar ratios. And if we look at this reaction, it's a 1-to-1 relationship between the F2 and the H2. So that means that we can say over here This is 1.52 moles per liter. Okay? And again, it's negative 1.52 because we're using it up. Remember, we're shifting to the right. So we're using these two things up. And then that would give us the equilibrium value for H2, which again would be the same. It would be 0.48 moles per liter. Okay? And then finally, we have this last one. But if we look at our equation, it's 1 to 1 to 2. So if this was 1.52, this would have to be 3.04 or 2 times 1.52. Okay? So it's if there's a 1.52 change in the F, that results in a 2 times that, a 3.04 change in the HF. And you'll notice also we're going to change the sign, and please get in the habit of putting the sign on these changes. This is a positive change. We're making this one. So then when we add 0 plus 3.04, we end up making a concentration of 3.04 moles per liter of HF. Okay. And at this point, I'm perfectly fine with you just working your way through that. You could, if the ratios are bothering you, you could set up some ratios. Someone wants to see it where I write out a ratio for each one of those things that I calculated. Just let me know in the comments and we will do that. But that's basically how you work that puzzle. You'll be given something initially, and then as you go through it, they'll either have to tell you one of the changes, and then you can move the changes using stoichiometry to each of the other columns, or they'll give you one of the equilibrium values. You'll be able to work backwards, get the change, and then use that change to find the changes in the other two remaining reactants or products. Okay, so that's how you would work that first question using an ICE table. Okay, let's try a second one here. It follows the same process, but we'll work through this one together. You have this one on your lecture question sheet. You may want to stop the video, go try it, and then come back and check to see whether your answer matches what I was doing. Or just follow along here and we'll do this one as well. So if you want to pause the video, do that now. Otherwise, I'm going to start into the answer. So when we look at this one, it tells us a few different things. We have 4 moles of NH3. It's not a concentration, but it's in moles. It's introduced into a 2-liter rigid container. So the rigid part tells us the container's not going to change shape. It's always going to be in this 2-liter size. And it's heated to a particular temperature. So that means the temperature is going to be constant. We don't really care what the temperature is as long as we know it's being controlled. And the amount of ammonia changes as shown in the graph. So we have this NH3 will be in equilibrium with N2 and H2. And if we put some 4 moles of NH3 into a 2-liter container, we get a graph of NH3 concentration that looks like this, which is similar to what we were drawing earlier last week, where we start out with just the ammonia. The ammonia is used up over time, and then it slowly levels out, and we know that we've reached equilibrium when we get to that point where the graph levels out, because that now it looks like macroscopically at least nothing's changing from this point forward. So this is the point that's at equilibrium, and before that it was shifting. The equation or the reaction was shifting to get to this equilibrium point. And if we look at the NH3, it was being used up, which makes sense again. If all we have is 4 moles of NH3 and we have none of these two things, then the reaction is going to shift in this direction because it has to make up some of the products and some of the reactants. Eventually, these two reactions, the forward and reverse, will get equal to each other again. But in the beginning, the shift is away from the ammonia and toward the N2 and H2. So we know then that this 4 moles is going to go down, and we know that both of these are going to go up. Okay, but it does ask us to determine the equilibrium concentrations of the other two entities. Now we have the equilibrium concentration of NH3 right here on the graph. So we see it levels out at 2 moles. So we can take that 2 moles and we can turn that into a concentration without too much trouble. So we have 2 moles of NH3 at equilibrium. But let's put all that into an ice table again so we can have a look at it. Okay. So we've got our table here. We need our initial concentrations, and we had NH3 right here. I'm going to put my little arrow there so I remember that that's where the reactants and products divide. N2 and H2. And we know that in the initial concentrations we had, no, not 4 moles actually, we can't do that because we want it in concentration here. So we have to do a little bit of math on the side. We know it's a 2-liter container. So if we remember that concentration equals moles over volume, and that would mean that we would have 4 moles over a volume of 2 liters. So we would end up with 2 moles per liter being the concentration, okay? Not 4. So what we put in here then is 2 moles per liter. And there were none of these things, 0 of this and 0 of that in the initial, okay? The next row we always put is the change. We don't know what the change is yet, but we are given one equilibrium value. So we can solve this table. And the equilibrium value here, it says there were 2 moles present at equilibrium, but it's 2 moles in a 2-liter container. So at equilibrium, there was only 1 mole per liter of NH3. Okay. And now we've got a problem just like the last one. It's just once we get that data set up, it becomes a little easier to solve. So 2 take away something becomes 1 mole per liter. Well, then the change must have been minus 1 mole per liter. All right. Now, if we were to move to this next column, we're going to go from the NH3 to the N2, and we see it's a 2 to 1 ratio. So you'll have to set up a ratio. If you can do this in your head with these questions, that's fine, or you can set up a ratio to solve it. But if there is 2 to 1 ratio, then if this changes by a factor of 1, this is going to change by a factor half that big, and it's on the other side of the equation, so it's going to be a positive. So we're going to have a change here of positive 0.5 moles per liter. Positive because we're making it. Remember, we figured out that our shift would be in this direction. And so that means we're going to be making some N2, and we're going to make 0.5 moles per liter of it. And then the last one, we're going to go from the 2 all the way over here to the 3. So it's a 2 to 3 relationship. Okay. So you have to take that into account. Now we can do that if you want. We can do that 2 to 3. I'll just write it out. How I usually do this is I just say I just do moles. If you want an easy way to write it out, I just do moles over coefficients. And in that first one, right, I'm moving from the 1 here. So I'm going to do 1 mole over a coefficient of, what's the coefficient on that one? 2. And then we say that equals, well, we don't know what it equals in moles per liter. Sorry, this should be moles per liter. We don't know what it is in moles per liter, so we're just going to put in H2 here. But we do know the coefficient in front of the H2, which is a 3. Right? If we set up that ratio, if you can't do this in your head, just set a ratio up like this, and it becomes, we just cross multiply. So 3 times 1 is 3, and 2 times H2, and then H2 comes out to equal 1.5. Okay, so that means then we're going to undergo a change here of 1.5. It's on the product side, so it's positive 1.5 moles per liter. Okay, and then to get the remaining values, we just add down. So 0 plus 0.5 means that the concentration here is going to be 0.5 moles per liter. And the final concentration of H2 is going to be 1.5 moles per liter. Okay, so I'm kind of quickly using a few things here, a little ratio to move coefficients, to use the coefficients, excuse me, to move the concentrations. I quickly used the volume calculation up here. Concentration equals moles over volume. So you may want to go back and just review a little bit of that or ask some questions, and I can post some things about that again. The other way you could have looked at this one is if you know this change was 0.5, it's a 1:3 ratio between the N2 and the 3, H2. So 0.5, well, 1:3 would be 3 times 0.5, which is 1.5 moles per liter. So if you want to, there's an easier way just to think about what this last concentration should be. Okay, so that's how you use an ice table. We're going to add a little bit of change to it because I've got to show you one more way of doing it where we don't know C and we don't know E. And there is still a way to solve that, and that's what we'll get into in the next video. But for now, we'll leave it there. Thanks.